Hi, welcome to this lecture on the Reynolds transport theorem for energy equation. We're picking up kind of where we left off. We talked about the energy equation, and there it is there. And now I wanted to introduce the minor losses. So last time we talked about the major losses and Darcy friction factor and whatnot. And the minor losses, if you recall, can be expressed in this way. The sum of the minor loss coefficients times the average velocity in the pipe squared divided by 2g. And that adds to the total friction loss, total friction head loss. And the way you got this was you counted up all of the bends and the valves in the system, and that's what the minor losses are. They are the valves, the bends, the flaps, the flanges, everything that might contribute to losses in the system that aren't necessarily associated with friction. These devices can cause swirls in the flows and eddies, which essentially act like a resistance to the flow field. So the way it works is you have a device and you can just look it up. Oh, a globe valve for a 2-inch screwed pipe is K equals 8.2, that sort of thing. Now I noticed when thumbing through the NCEES handbook, there were no minor loss tables. So it makes me think maybe there's not going to be that much minor loss on the current incarnation of the FE exam. But if there would, they'd have to give you the K value in the problem statement. All right, so let's talk about the hydraulic diameter. What the hydraulic diameter is that in order to handle square pipes or rectangular shaped pipes, we want to find the equivalent circular pipe, and then we'll do the whole example on the equivalent circular pipe. We'll do that whole problem that way. So by definition, the hydraulic radius is the cross-sectional area of the pipe here divided by the wetted perimeter, meaning the length around the pipe. So you can see it's area divided by length, you would get a length. So what's the hydraulic radius for a box that has alpha on each side? So this thing is a square. Which one of those would you pick? Well, it's easy enough to calculate this. The area is alpha squared, and the wetted perimeter is 4 alpha. Cancel it out. You get alpha by 4. There's the hydraulic radius. Couldn't be easier. But what we use in the calculations is the hydraulic diameter. Mostly when you do pipe flow analysis, the Reynolds number is based on diameter, so you need the equivalent diameter. And this is where things get weird. The equivalent diameter is 4 times the hydraulic radius. What? That's true. That's always on the FE exam in some carnation. So keep that in mind. Now, why is that? Well, it's because if you did this for a circle, right? So if I got a circle there, and the diameter is this psi variable here, and I went through and I calculated psi. The hydraulic diameter is 4 times the hydraulic radius, so that's the area is 2 pi r divided by 4. Did I say that right? The area is pi d squared divided by 4. The perimeter is 2 pi r, or pi diameter. And so if you look at this, right, the pi's cancel, the 4 cancels, you cancel, you're left with just psi. That's exactly what this diameter is. So that's why the hydraulic diameter is 4 times the hydraulic radius. To make a circle makes sense. Also, recall your pipe system definitions, pipes in series versus pipes in parallel. So if you have a pipe in series, the mass flow rate in each section must be constant. So you would say the mass flow rate of 1 is equal to the mass flow rate of 2 is equal to the mass flow rate of 3, which would be equal to the whole mass flow rate from A to B. The head loss through each section adds. So you would add the frictional loss here, and the frictional loss here, and the frictional loss there, and that would be the total head loss from A to B, including the major and the minor losses. Now for parallel pipes, it's just the opposite as it is for series pipes. So the total mass flow rate from A to B is equal to the mass flow rate of pipe 1 plus the mass flow rate of pipe 2 plus the mass flow rate of pipe 3. See, that expression is very different than that expression. and the head loss are each equivalent. So it's kind of like the mass flow rate in the series pipes. So what happens is that when you first start up the system, maybe the flow rate wants to go down this pipe. The flow rate would increase until the friction got so large that flow would rather go along this way or along this way. And in so doing, the system rapidly comes to equilibrium. So which way the flow decides to go down this branch of parallel pipes becomes the same resistance to go each way, so the system is in equilibrium. So the head loss from A to B is either, you could calculate it as either the head loss from pipe 1, which is equal to the head loss through pipe 2, which is equal to the head loss in pipe 3. So these are like your, resistors in parallel or resistors in series. All right. Hope you enjoyed it. Hope you learned something. I hope you do well. Try some practice problems. It's the best way to learn.